Okay, so then a few more reactions. Excellent. So James is going to ask the same question. I would give you the same answer as well. Okay, so now when thinking about some other reactions, you can carry out the same sort of chemistry with sulfur. You could use this really foul-smelling reagent here of this ethane thiol and react this two equivalents with the ketone to generate the acetal, and this is known as a thioacetal. And this is particularly useful because you can use also this foul-smelling ethane, ethane dithiol. Yeah, this one smells really bad, these sulfur reagents. But you can use it to react with a ketone to form, again, this thioacetal. The question is, why would anyone ever want to do this? And short answer is, I don't know. But the longer answer is, you can use this to remove a carbonyl group. So we had the Clemmensen reduction before. Let's just put this here for a comparison. That's spelled right. Clemmensen reduction, where you had a carbonyl group to stick with acetone, and you treated it with zinc, mercury in the presence of acid, HCl, and then this got rid of that carbonyl group, replaced this with hydrogens through a mysterious mechanism. Maybe you don't want to do that. Maybe your compound is not stable to concentrated HCl. You oftentimes have to heat this too. So this is pretty vigorous in terms of condition. And what this means is this is an amalgam. It's a mixture of zinc and mercury together. And maybe you don't want to work with mercury because of its high level of toxicity. So instead, you have a carbonyl group that you really want to get rid of. So instead of working with mercury and HCl, you're going to work with this very foul-smelling ethane dithiol. And you can form this cyclic thioacetal. And then through another reaction that we're going to leave as a mystery, you can actually treat this with something that's known as rainy nickel. And this makes the thioacetal be substituted with two hydrogens. So we have two ways of getting rid of a carbonyl group. Now, we have the Clemmensen reduction and the thioacetal with rainy nickel. What this is it's the metal nickel, and it's named after this person named Rainy, I think. And so it's a nickel infused with hydrogen. So it's like the catalytic hydrogenation where you would use, remember, hydrogen with platinum, palladium, or nickel. This is a way of delivering hydrogen. So that's where these two H's come from, these two hydrogens. The metal surface has the hydrogen absorbed onto it. And this actually is a really nice reaction. Once you get over the smell of the thiol reagent, you can just sprinkle in the rainy nickel and it works pretty well with some solvent. So if you're looking to get rid of some carbonyl groups, now we have two ways to do it. And again, this actually is useful in synthesis. So you might have a carbonyl group that you use to introduce a carbon-carbon bond, and then you want to get rid of it. There's one more. There's a number of ways. There's one more that we may get to. I don't think, we haven't talked about it yet, known as the Wolff-Kishner reaction. But we can do it under acidic conditions. We can do it under neutral conditions, here with rainy nickel. And then there's another reaction that will do it under basic conditions. We'll just slowly scroll up. Yes. So, a couple of things here. Why are living organisms so easily harmed by heavy metals? The music or the elements, I think. Yeah, okay. I grew up in the 80s and 90s, and so that was all the rage. One of the things is with, showing my age, I think. So with mercury here, trying to think of a couple of things to explain with this. Thiol reagents, okay, also the old name for a thiol reagent was a mercaptan. And this actually is relevant to your question. And this is like a like a lover of mercury in a way, because you know how nucleophiles and electrophiles, they have their names, and so the mercapto species or mercaptans, they really like to interact with mercury, and it has to deal with what's known as the softness of the sulfur and it's what's known as a soft metal, which you may have seen in Gen Chem or something like that. So mercury really interacts well with sulfur, and so it just takes a small amount of mercury to form a complex with the sulfur. Well, we have cysteine in a lot of very important places in proteins, and that's one of the things that mercury can do, is it can bind strongly to the cysteine residues in different proteins, and it takes the place either of other metals that may have been bound there, like nickel or something like that, or it just blocks a lot of function of proteins. And so once you end up forming these sulfur-mercury bonds too, it's not going to be very interchangeable, and it can also, so then it can accumulate as well. And so that's one of the reasons why a lot of these heavy metals, things like mercury, cadmium, and so on, are very toxic, is because they interact very strongly with sulfhydryl groups in proteins with cysteine. And so if we have some protein backbone and you have the amino acid cysteine, you have the sulfhydryl group there. So those are oftentimes not just dangling out into space for nothing, right? You know, they're involved in disulfide bonds, important for protein structure, and also coordinating metal ions. And a lot of times when you see cysteine residues, they're coordinated to nickel and things like that. All right, so we could go on and on and on with that. But in the last 5 minutes here, let's just set the stage for what we're going to do next. Yeah, I think that'll be a good thing. All right, so now, one of the sorts of biomolecules that we actually want to talk about here in our organic class are carbohydrates. And we'll see sugars everywhere, and we're going to talk about them more for their structural properties here. I think I found somewhere on the internet, so it must be correct, that 50% of the dry weight of the Earth's biomass is of polymers of glucose. So things like cellulose and starch. So glucose in one form or another is everywhere. So this is plant and animal matter. And I'm sure we all have varying levels of affection for glucose and other sugars. So what we want to do here is to think about these carbohydrates. Not necessarily, we don't have to memorize all of the 20 common sugars and things like that, but we're going to focus on these 4 things that I have here. The types of carbohydrates, so we can recognize them, and notice the language is what we've already been using. So we're going to have aldoses, we have an aldehyde, like this glucose up here is an aldehyde, and ketoses. So it's probably going to be something that has a ketone or a carbonyl group. We're going to focus on stereochemistry, because one of the issues with carbohydrates is there's a lot of new terminology that's specific to them. Rather than using R and S, there's a designation of particular stereochemistry that focuses on, that's the letter D. So there's D and L. We want to think about conformations. This is probably the hardest part to visualize. We're going back a little bit to stereochemistry and the mental gymnastics that you play with conformational analysis. And we want to think about acyclic versus a cyclic carbohydrate. And then in terms of the reactions, we've already pretty much seen the chemistry that we're going to look at. It's going to be formation what's known as a glycoside, and then a couple of others as we get to it. So really quickly here, in terms of the structures that we want to use with carbohydrates, just to think about it, is this would be the bond line structure of glucose that we've seen. And one of the challenges when dealing with carbohydrate is there's all these hydroxyl groups, stereochemistry. Notice it's chiral. We have 4 chiral centers. So we're going to be using some different ways of drawing these structures. And I think you may have seen this in OChem 1 just very briefly. So one way of drawing these is we have a Fisher projection. So I'll draw the Fisher projection here for glucose. We're going to use glucose 100 times. And we'll go through this process next time. But we want to get used to thinking about this in terms of the Fisher projection. So next time, as I mentioned, we'll go through how we convert from one to the other. We want to think about this in terms of what's known as a Haworth projection. glucose, I'll draw the beta, which actually now represents, notice, a cyclic structure, Hayworth projection. And then I'm sure everyone's favorite, the best representation of this actually is the chair conformation. It's one of the glucose chair conformations. And we want to be able to interconvert between each of those different conformations because they represent different things. So the chair is capturing the most information. However, sometimes it's kind of annoying to draw this like this, and so we'll just use what's known as this Hayworth projection. And what you'll notice is that most common sugars are 5 and 6 membered rings, because we saw in organic 1, those are the most stable structures. So as I wrap up here, I'll leave this up so that you can write that down.